So, I regret to inform, today's class is going to be one of those classes. Today we are primarily doing definitions. I know. And the worst part is, like, these definitions are going to be, like, pretty strongly what a fair amount of questions on the midterm are going to be based on, so pay attention, everyone. I will try to make the definitions lecture interesting. This is a recorded class, yes. I am recording. So. Oh, this is a nice little point. Yes?
Are you doing any SQL queries today or not? Because I'm running it on Docker and it's completely bad. Should I stop it? Or
You should stop it. Yeah, I don't think there's actually like well, right towards the end we're going to create a table, but aside from that we're going to be doing mostly definitions. So, yeah. Okie dokie. There we go. So, this is a class on relational databases. It may interest you to know what a relation even is. A relation is a table with rows and columns. So you remember what I was like doing with the wibbly wobbly cloud of natural numbers and like a mapping between that and another wibbly wobbly cloud, right? It's relation in that sense. So basically, the mapping itself in mathematics has three terms that you can use to describe it, right? A function, a relation, or a mapping. There are like academic differences between these terms, but generally they all refer to the same thing. So in this case, when you're talking about a table, you're talking about a relation between, for our purposes, a thing we're going to discuss called the primary key and other domains. Right? Make sense? So, good. Each row contains information on an instance of an entity. So, records are instances, right? This is an instance of an entity. Vasily Jandel, male, at 770 Pleasant Avenue in Hamilton, Ontario. That is a particular instance of the entity represented by this table. So entity, for those of you, we kind of introduced the idea of an entity last time, but if that concept is not yet solidified, what an entity is, it's the thing that you're trying to track with the table, right? A lot of the time, it will just be the table's name, right? You name the table after the thing you're trying to track. This is the patient's table. So, patient is the entity we are trying to track with this table. Does this make sense so far? So far, so good? Any questions? Okay, good. So, a row within a table can also be called a tuple. The correct pronunciation is tuple. Anybody who says tuple is wrong. It is tuple. You find tuples occurring in Python as well. That's probably the only other place you've seen them. Has anybody encountered tuples in Python? Anyone? No? Okay. Well, Python's a bit more complicated than you guys covered in your intro programming class, as I'm sure you're not surprised to hear. Python has implemented, I can remember 4 major aggregate data types. you've got lists, right? You've also got dictionaries, you've got sets, you've got strings. Strings are an aggregate data type. And then you've also got tuples. So in Python, what distinguishes a tuple from an array is that tuples are immutable. So once you've declared one, you can't change it. You can destroy it, make a new tuple from that data, right? Then you have a new tuple, and you dispense with the old tuple, but you can't directly modify a tuple, right? So hopefully that gives you some kind of idea what a tuple is, but all a tuple is really is it's a collection of data, right? A collection of data arranged all in a row. Make sense? So far so good? Any questions? Snip, snap, snooze? Scoodlebot do? A column in a table is also called an attribute. Attributes in tables are, you can think of them as being very similar to instance variables in a Java object sense, right? When you declare an instance variable in an object in Java, you're saying, okay, all objects of this type probably have this property, right? The attribute in the table is a similar kind of an idea. Make sense? Still no questions? Yeah, good, okay. Primary key. So the primary key is somewhat important, hence its primacy. So when you have a table full of data, one thing that's extremely useful is to be able to pull out particular element from it. Uniqueness is a very useful property to have in a table, right? So the problem with these data, right, all of the rest of these data, is that they don't necessarily guarantee uniqueness, right? Certainly not gender, right? Gender, in our formulation, only has 3 possible values, so it's impossible to uniquely determine a person by their gender. Even name is not uniquely determining, right? I can certainly tell you from experience within the college system, having worked in this college, like, the reason I need your student number when you email me something, right, is because I sometimes even get people with the same first name and last name in the same class. That happened once, right? So I do, like, especially if you're asking me to, like, look something up that's not, like, from the course shell, I do, like, the student number is your unique identifier, but your name is not a unique identifier, right? So, when we create a table in a database, it is often useful to have one column dedicated to just that, a unique number for every entry. This is known as the primary key. Does this make sense? It's often called something something underscore ID. So in this case, patient ID, identification number. Make sense? So far so good? Very good. So, an attribute whose value determines the value of another attribute is called a determinant. So, for example, I can't actually, this table doesn't represent a good example of this, but let me give you another example just from in my brain meat. So let's say we had a table that was departments, right? Departments in a hospital. And one of the attributes in that table was the room number of the office for that department, right? That's very useful information to have in the table, but each department only gets one, and it's unique for that department. So, in a sense, the primary key determines the room number for that department, right? Another good example is if any of your columns are calculated using a formula, then the determinant column, then whatever variables go into that formula, those are the determinants for that column, right? Make sense? So, for example, if we were, this is kind of a silly example, but I'm going to say it anyway. Imagine we had a table for like geometric objects. Oh, Java's back. Imagine we had a table for geometric objects, right? Let's say we had, width and height as attributes of the table. Perimeter, if we're talking about rectangles, right? Perimeter, it could be useful to be able to just say, give me the perimeter of square with ID 73, right? That could be useful. Perimeter is not new data, right? It's not unique data. It's data that's calculated from other data. The things it's calculated from, in this case width and height, are determinants. Does that make sense? So far so good? Any questions?
Yeah.
Yeah.
You said like the attributes of the table would be the width and height, but I thought that an attribute was merely like data arranged in a column.
Yes. Well, those would be like,
if you had a column for width and a column for height.
yes. So this is kind of what I'm imagining, right? You have an ID number, you have a width, you have a height, you have a perimeter, maybe you have an area too, right? And then you have, 10, 11, right? And then, right? You see where I'm going with that?
Yeah.
So like, this attribute would be width,
Yeah.
right? But yes, the concept of like, let's go back to the attribute slide. So, I think that your question does kind of fall a bit into the gray area of the definition, which is given here. Like, is it a property of the entity, or is it the collection of all data associated with that property of the entity? That's the question. And I'd have to look it up. But that's kind of where, yeah. You understand what I'm saying though?
Yeah.
I don't think it's incorrect to refer to either as the attribute. Width is an attribute of a rectangle, right? These would be the values of the width attribute of that rectangle, or the last names of the patients, right? Very good. All right. Functional dependency. That is the relationship between a determinant A and a dependent attribute B, represented by A arrow B. So I think, I don't like that example as much as my own. Yes?
So, that one right there, you've got width and height, and
Yeah.
then you've got perimeter, which is calculated based off the width and height, would that be a functional dependency?
Absolutely. In fact, we can tell you what the function is. Right?
Yeah.
So, yes, functional dependency. So in my case, I have two determinant attributes, which are both contributing to perimeter and, also to area, but let's just talk about perimeter, right? Yeah, so yes. So in my case, I would have something like width, comma, height gets perimeter, or depending on what notation you're using, it could also be width cross height gets perimeter. Both notations would be fine. This is more of like a computer language way of saying it. This is more of like a set theory notation way of saying it. But they're both equivalent. Make sense? Question?
So the width and height depends on the ID, and the perimeter depends on the width and height.
Well, see, to an extent, yes. To me, right, it all comes down to like how you want to characterize the function, right? If your function is a formula, that to me makes it most clear, right? Like there is a formula by which these two values are related here. This would be a mapping, but I couldn't like point you to a function, right? There's no mathematical equation which I can write down that will tell me what the first name is from the ID, right? All we're doing is associating keys with values. So an association of keys with values, to me that's more of a mapping. But again, mappings and functions are interchangeable terminology. Does this make sense? Okay. Man, this class is a lot mathier than I thought it was going to be. Lots of set theory stuff. Question?
I have an issue with the candidate key slide, actually.
The candidate key slide, okay. Is that one we already did, or?
It's the next one.
Okay, all right.
It says that a candidate key is an attribute that could be used as a primary key, and it uses the health card number as an example. But I don't believe that that would work as a candidate key because it has the opportunity to be entered as null.
You could have multiple nulls.
Ah, I agree. Well observed. Yeah, true. So,
If it was required for a health card to be submitted for someone to be entered into the database, then it would be a candidate key, but
Yes.
because it's not in this example, it wouldn't really be enough.
what we are eventually what this discussion comes down to are what constraints are placed on this column, right? So, in order for it to be a candidate key, a couple of things have to be true. Number one, all values in it must be unique. This is the issue we ran up against if we were allowing null. So obviously we can't allow null because null would be non-unique. So this column must be required to have something to be a candidate key, and all of the things inside of it need to be unique, right? Make sense? Honestly, like if you took patient ID and multiplied each value in there by 2 and made a new column for that, that would also be a candidate key, right? Every value in there would be unique, they would all exist. But that would be derived, right? That would be derived information where, the health card number isn't really derived from the patient ID in this case, right? Although, I would say that, this is kind of a problem that I have with the slides. You'll find that I spend half of the time in any class I teach arguing with the slides. I would say that you could make as much an argument that the health card has been derived from the primary key as the first name has been derived from the primary key.
Yeah.
All you're really saying is that the data has been associated with itself, right? You're not really, not saying much.
Yeah.
All you're saying is that these two things exist in the same row, right? But yeah, if it is a requirement that every patient have a health card number, then this would be functional as a candidate key. Health card numbers are unique for every person in the province, assuming that this is an OHIP card, right? I think that follows OHIP, right? So if it's an OHIP card, then, well, at least every person in the province who is eligible for the OHIP program, you see where the gray area comes in. So if we say, if we build a hospital and we say, okay, you're only allowed to be a patient at this hospital if you have an OHIP card, right? Then the OHIP number, which is uniquely determined for everybody in the province, will certainly be uniquely determined for everybody who goes to your hospital, assuming that, the people in your hospital are a proper subset of the people who are in the province. You also don't have any out-of-province patients. Yes?
But if you use someone's SIN number, would
Yeah.
that work as what do you call it, a candidate key? Some SIN number would be all unique and everyone should have a SIN number corresponding to them.
Yeah.
Yes, absolutely.
As long as it's a required field.
Yeah.
Yes. As long as, shading into, as long as your organization has the right to collect SIN cards, and as long as you think it's a good idea to associate SIN cards with people's names in a database, right? That's kind of where you start leaning with that kind of, we have to be a little careful about what sort of identifying information we keep in our databases in case those databases become breached, right? SIN card is another good example, and that's that would be Canada-wide. Yeah, yes.
So is a candidate key like a unique identifier for an entity?
Yes.
Essentially, it's something that could be used as a primary key.
If we didn't have a primary key, we could use that instead of a primary key, right? Now, the reason that we don't, right, here's the thing, all right? Is this an integer?
No,
No.
What is it?
it's a string.
It's a string. It has letters in it, right? You folks know anything about the speed of string comparison in comparison to integer comparison?
Well, seeing a string is a class and not a simple variable, it's going to take a lot longer.
The term I would like you to use is aggregate data type. So, because in order to compare a string to another string to determine if it's the same string, you have to compare each character in both of them. You have to run a loop every single time you do it. Integer comparison, built right into the CPU.
Is this equal to this?
Boop, yes, no, yes. It basically does the same thing with bits, but it does it all at the same time, right? So, for speed, you want your primary key to be an integer. It's also useful, it can be useful to have them in order, You'd be able to, make a couple of approximations and, find data out in certain ways. Like if you start at 1 and the number of, you have 1 for every person, the largest number in here is the number of people that have ever been in the database, right? Because if you have records sort of being added and being removed, right? That's the total number of people that have ever been in the database. Yes?
If there is another candidate key that is a string, would it be a better idea to create basically an arbitrary number for for everything in the database to be the primary key? Like you're looking for an integer, or would having an arbitrary value be?
No, having an arbitrary value is not a bad idea. In fact, like there are some reasons to use sequential numbers. There are other reasons not to use sequential numbers. Although I can't think of any at the moment. We have a slide on this coming up though.
It's the next slide.
Ah, there you go. Thank you. So, primary key, first of all, important that it's not null. Hopefully that's obvious. Everybody, yeah? Good. A good choice for primary keys is meaningless but unique number. So if you start at 1 and keep incrementing, then you get, what is that? 2,147,483,647 possible values in your database. If you use big int, then you can have 9 quintillion over 9 quintillion entries in your database. So, but another possibility is a globally unique identifier. Also universally unique identifier. So in SQL databases, the way they usually do this is it's a 128-bit integer, typically expressed as hex digits. So, okay, here's an important thing, guys, all right? You guys know hexadecimal? Yeah, a little bit?
We were just learning about it in the Math for Computer Studies class.
Okay, so please note, although this looks like a string, is it a string? No, it's a hexadecimal number. So these letters aren't actually letters, they're digits, right? So this is good for decentralized systems. Likely unique forever. So we can have a little bit of a conversation about cryptography. So, what does it mean that this number is likely unique forever?
That there are like nearly infinite possible combinations, and once a number has been generated, it's unlikely to be generated like ever again.
Mm-hmm. So, the probability of randomly generating a number which has been used before is very, very small. Not 0, but very, very small, right? So small that we approximate it as 0, although it's not actually 0. We're going to see, those of you who are taking server-side with me, we're going to see this type of thing pop up again when we talk about cookie values and session IDs. So let's just take a moment to do a little math. All right? So we know that this value is 128 bits. Do you know how you've been taught how to determine the largest number you can express given the number of bits in that number? Anybody? Just unsigned arithmetic. Don't worry about signed arithmetic.
The number of bits that you have in a number.
2 to the power of the number of bits. That's right. 3.4 times 10 to the power of 38.
So quite a bit.
There's a lot of zeros. Yes. So is anybody aware of like how many atoms there are in the universe?
Probably over like one Google or something.
And one gold, you know, or no.
10 to the 80. Right? So we're not there, right? But we're kind of in the same. Well, actually, we're not in the same ballpark at all. But you know, we're talking about really big numbers.
If you added zeros, you'd be about like halfway there or something.
Yeah.
It's more than the amount of stars in the observable universe.
There you go. How about the number of seconds since the Big Bang? Oh, there you go. Okay. Number of seconds since the Big Bang, according to AI, I guess. Yeah. 432 quadrillion seconds, according to Reddit. Well,
Honestly, the FBI probably pulled it on from that.
yeah. Okay. Well, let's just assume that the AI is correct.
Apparently, Reddit is the number one source of where
I think
Google
you
AI
can say
cites
that.
its data from, which is
Why didn't we do
concerning.
that right?
All right. I'm sorry. I had to psychologically block that statement to maintain my own sanity.
I remember a pretty funny thing in the gaming sphere a little while ago, where for a particular video game called No Man's Sky, there were a bunch of people who wanted to play a prank on Games Media and started talking about some made up stuff on the No Man's Sky subreddit. And sure enough, a few days later, an AI generated article from one of those Games Media questions made an article about the made up thing they were talking about and reported it like it was true.
Okay. So, if you take the number of seconds which have elapsed since the universe began, and you divide that by the number of possible numbers that you could generate randomly using 128 bits, you get this number. That's the number of times you'd have to rerun the universe over again, generating one number per second to get that number back again. Now, you could probably generate a lot more than one number per second. You know, maybe you can generate 1 trillion numbers per second, right? Take that whole thing, divide it by, 10 to the power of, is it billion is 9? No, yeah, million is 6, billion is 9, so 12, 10 to 12. Right? That's the number of runs through the universe that you would have to do before, you probably hit that number again. It's a long time. It's a very long time. It's effectively infinite, but not infinite.
Inconceivably long.
Yes. These are numbers so large that we mere humans in our poor human brains cannot possibly conceive of them. Yes.
Speaking of hexadecimal,
Mhm.
couldn't you use a candidate key as a primary key if you get rid of this string comparison by just making the candidate key a hexadecimal number? That way even the letters have numerical values.
See, the problem that you then run into is like the compactness of the format. So, effectively, the largest string, like the integer comparison in the CPU works on whatever the word size of the CPU is. For us, 64 bits. It's been 64 bits for quite some time, actually. That's because, this is the number they hit that was finally, good enough that they don't really need 128 bits, right? So, 64-bit architecture can compare a 64-bit integer to a 64-bit integer, right? In order to take the health card number, render that like the number of numbers in it, if you take each character to be a number, is actually quite large, right? Every a character, assuming the characters are 8-bit encoded, that means each group of 4 characters is one integer, assuming integers are 32 bits. So it still doesn't work. You're still exceeding the word size of the operating system, which means that you're not gonna be as effective as just straight integers. But I do agree that that would help tremendously because you're no longer dealing with strings.
Although there is also the argument of for for example, a hospital ID, you could just have it be 128-bit integer, but it's a lot easier to just type 1042 into the keyboard.
Yeah. So here's the reason you would use this over the other one, right? Let's imagine that you're not a hospital. In a hospital, you can presume that your database is like a computer in a closet somewhere, right? Central database. What if you wanted to do a unique identifier for Facebook posts?
Like Google.
Yeah, or something with Google, right? If you wanted to do unique identifiers for Facebook posts, real world problem, right? Do you think that Facebook has one database? No. Right? It has many databases. The disadvantage when you're distributing it here, to number things sequentially, you need to know what the highest number is, right? Which means you need that access to this one database. It works if you're centralized, but if you're working with a decentralized database, then the ability to generate a random but valid key is very, very useful. And you can do that from anywhere, right? Make sense? So far, so good? Good. So, SQL Server provides an optional entity property to simplify creating embeds. That's the first one we talked about. The identity property would be added to the definition of the primary key column when the table is being created. So we haven't discussed table creation syntax yet, but it's a lot like declaring a function. You say what the name of the attribute is. You give it a data type, comma, name, data type, comma, name, data type, right? The difference in SQL, you can add additional constraints at the same time as you're defining the data types. So one of these constraints is identity. You can label one of your attributes as an identity. Seed and increment are both optional, defaulting to 1, but if you want your IDs to start at 10,000, you can have them start at 10,000. Make sense? So far, so good. Any questions? Okay. Using the identity property is highly recommended. If you wanted to create a sequential ID number without using the identity property, anytime you insert anything into the database, the first thing you would have to do is perform a select query out of the database to see what the next number should be, right? As opposed to just having the database keep track of it itself. So when you have specified that an attribute is an identity, you do not include it when you insert things into the database. It will be automatically kept track of. Does that make sense? Good. So, shall we take a moment to just breathe before we get more definitions? I am a leaf floating on a still pond. I am the reflection of the moon in a stream. Shall we continue? Atomic attributes. This is our most explosive topic yet.
like that.
An atomic attribute is a component of the record definition that is used to describe an entity. Atomic attributes only really make sense when you consider them next to composite attributes. So, we said that an attribute is a column, right? But some properties of an entity require more than one column, or at least we usually put them in more than one column. The best example is an address, someone's address, right? Street name, province, postal code. These are all different fields, right? These are all different attributes, but together they kind of form only one semantic whole, right? Like the address is a property, but it's described to us by multiple attributes. So, the address is a composite attribute. Does that make sense? First name, last name, those are a composite attribute, right? Let's take a look at our data again. Actually, I think that's the only two. Those are the only two here, I think, unless somebody else wants to, like, link something together. But, like, name is composed of first name and last name. Address is street address, city, province, postal code. An atomic attribute is essentially anything that's not that. Right? Anything that's not composite is atomic. Atomic just means it stands on its own. It is an atom. It is an indivisible attribute. Does that make sense?
So in terms of an address, what would be the atomic attribute there?
Oh, well, if you address wouldn't be an atomic attribute, but email is,
Okay.
right? Because, I mean, unless you were to take email and say like the front bit is one column and like the back bit is another column,
Yeah.
but you wouldn't do that, right?
Would
Yes.
that work is if like you're doing like, let's say at gmail.com, but then there's also like at Hotmail, like the people are under like different mail like registers, like that?
Mm-hmm. Yes, if you took the register, as you say, although there's probably a technical term for this, but I don't know what it is. If
That's like what my work calls it, like at my
domain, maybe?
work. Yeah, it's kind of
Yeah.
like domain, but we call it register because we sign up for like our rewards program at my I work at like in retail.
Mm.
It goes under a certain like register column. So
Yeah.
it's like if you're with Gmail, you go under a certain thing when you get our emails. Or
Oh,
stuff like that.
okay.
It kind of like we do it so we're able to find promotions easier, or like help customers find stuff easier.
Interesting. So in your case then, the database that you work with does separate the domain out from the front part of the email. So in that case, it would be a composite attribute. But in our case here, it's an atomic one. Probably the best attribute to consider atomic would be like health card number or perhaps gender, I think. Birth date is another. Well, see, birth date you could break down as well, right? You could do day, month, year as different columns, right? But like this one's only a single character, so how are you going to break that down, right?
So just like a real atom, an atomic attribute is something that can technically be split, but really you shouldn't under normal circumstances.
Yes. Yes, it's something that unless the splitting of an atom is taken with great care and delicacy and a great degree of technological support, will cause untold destruction and devastation. Yes. Very good. Where are we here? Oh yeah. All right. There we go. So, derived attributes an attribute whose value was obtained by applying a formula or other data element. Perimeter, in this example, is a derived attribute. Very good. Multi-valued attribute, an attribute with multiple possible values. For example, an employee can have more than one skill. You can kind of think of it as like stuffing an array into one of these table cells, right? Alias, kind of like the whole database thing is kind of like, you kind of want to try to avoid using arrays in general, but like you can if you have to, sort of thing. Alias, or synonym, a different name for a data element with the same meaning. So, for example, in this query, we are counting the number of patients, right? Counting the number of patients. We are assigning it an alias total. So we can refer to the count in other places in the query as total instead of, it's very much like assigning a variable, right? Assigning it to a name. Does that make sense? Questions?
Basically you put the name, you rename one of the data elements, right?
Yeah, it's most similar to like a let binding, right? You should think of it as a binding.
Like this is the name we refer to, but is really referred to another thing, something like that?
Well, no, it's like I'm performing this calculation, and I'm going to give it that name, and I'm going to like the table that you get out of this query looks like this. It looks like that. As opposed to whatever the name this was going to be, right? Like, if you didn't alias it, the system would determine what the name of this column should be. Here you're saying, no, it's going to be total. This is probably a good idea because, for example, if you're running this query from PHP, right, it's good to know what the output's going to be called so you can look it up. You know, when you read the data, when you read the results of the query, it's like you know where to find your data. Does that make sense? Good. All right. Domain. The set of all possible values an attribute can take on. So, basically, domain is kind of similar to the idea of data type itself. Some mathematicians may say that you define a data type by its domain. So, what is the domain of the natural numbers? One, two, three, 4, 5. Some people include 0, some people don't. The domain of the integers, negative infinity minus 1, negative infinity minus 2. You know, yeah. Or I guess it would be negative infinity plus 1 and negative infinity plus 2. All of the whole numbers, positive or negative.
Real numbers, right?
No, that's integers. All of the whole numbers, positive or negative, is integers. Real numbers are the same but with decimal places. Strings, the set of all possible combinations of characters, right? What's the domain of Booleans? True and false. Very good. Concatenated key, also called compound key. We actually already talked about this. 2 or more attributes taken together to uniquely identify a record. So, basically, if we if we go back to our table for a moment, imagining we didn't have a primary key, and imagining we didn't have a health card number. I'm gonna do it on this board, I'm sorry guys, I've been neglecting you. Thank you. I hate this classroom. This is terrible. Any classroom that has to have more than one projector is bad. Bad classroom. So imagine we didn't have patient ID, and imagine we didn't have a health card number, right? It is still possible that in combination, some of these attributes would uniquely determine patients, right? Now, the slide says first name, last name, and if you have a date of admission or time of admission, that's probably going to be unique. Probably, right? It's not guaranteed to be unique. It is theoretically possible that two people with the same name arrive at the hospital to be simultaneously treated for the same thing. That is possible. But it's really unlikely, right? It's probably unlikely enough that this works effectively. It would probably be 10,000 years before that situation happened.
And
Right.
even so, you could just admit the second one like 1 second later and it's fine.
Precisely. Do you have a question?
No, it wasn't literally the same thing, like,
Yeah.
usually they have like record, not only day, hour, second also, so.
Yes, or even millisecond. See, the thing is though, the person doing this data entry is unlikely to be aware of that constraint, right? It's unlikely that the person who's entering the patients in would be aware that if two people with the exact same name were entered at the exact same time, this would cause a problem. So they probably would just do it anyway, right? So,
I was gonna say email could be used, but I remember that email could also probably be helpful, and that wouldn't really be helpful.
this is true, not everybody has an email. Some people share email. You can imagine like, I don't know if this really happens anymore, but like in the 90s, you'd have like a family email address, right? Several people would have the same email. All right. Good. Secondary key requires an index. Requires, I feel like there's a word missing in that sentence. Requires an index may not be unique.
Maybe needs a hyphen.
Requires that a unit index may not be unique.
It may be missing a comma.
I
Yeah,
was thinking another hyphen, like that might be another dot on it. Requires an index and then may not be.
yeah. Yeah, I think so. So, last name may not be unique. This is true. This means that it requires an index. So it's a secondary key, not a primary key. So I guess you could say that everything that's not a primary key or a candidate key is a secondary key. Foreign key. So, this comes more into it when we talk about joining tables, right? But essentially, some tables that you guys remember that that example I did last time where I had like the little table in between that linked tables and two other tables, linked rows and two other tables, right? You guys remember that? I'll do it again. All right. And maybe I'll use a slightly better marker. My markers, I've even been storing them upside down like you're supposed to, and they're still bad. That's better. Okay. So, let's say we have a table for cheese Alright? And we have a table for crackers. Right? So 1, 2, 3, 4. What's the type of cheese?
Mozzarella.
I was gonna say fromage, and I realized that's just cheese and French.
Brie, mozzarella. Yeah, I mean French cheese is different.
Blue,
Blue. Yep.
cheddar.
Blue. Hey, you have someone else.
Cottage.
Cottage. There you go. Cottage. There we go. Crackers. Give me a type of cracker.
Ritz.
Ritz. Give me another type of cracker.
Breton.
Breton. Yes. I say Breton, but if you want to say Breton, that's also fine. Triscuit. There you go. Wheat. So we have a table of cheese and a table of crackers. Maybe you, because you're mad, maybe you want to keep in a database every combination of cheese and crackers that you've tried. Right? Because we're mad. We're all mad because we're studying computers in the first place. This is not outside of normalcy for us, okay?
Just talking to your partner, just like, no, I swear there's a reason why I have a database with all
I've-
different combinations of cheese and crackers.
I tried that combination, it was bad. I have the data.
I imagine cottage cheese and Ritz would not taste good.
See, you might think that,
But is it in
but
your
you
table?
don't know.
Is it in your table?
Until you've tried it, you don't know. Science. So, tries, right? So tries, you'd have a primary key in there because of course you have a primary key. You have a primary key for everything. So let's say I tried Brie with a Triscuit and I gave it a rating of, 4, right? ID, cheese, and cracker. Right? Maybe next I decided to try some cottage cheese on the Ritz and found that that is indeed a -2. Right? Maybe I tried cottage cheese on a Breton cracker and found that that's still bad, but not quite as bad as the Ritz. Right? Make sense? So the purpose of these keys here is to refer to entries in other tables. These are in fact the primary keys of things in other tables. They are foreign keys, where foreignness is determined by locality to a table. Does that make sense?
Yep.
So far so good?
I appreciate that you have a primary key for the cheese and crackers chart. It's like, yes, I'm mad, I'm not stupid. Of course I have a primary key for the cheese and crackers.
You know, I actually have a primary key for my wife.
Well, that's a relation of an entirely different kind. We're gonna try to stay to food, and we won't make this like boys and girls or anything. Yes, entity occurrence, represented by a record with actual data values in it, or a row in the table. Row, I guess. It is an occurrence of the entity, sure. Ooh, I've got great big X's on this line now. See, this is why this room sucks. This room sucks, man. Like, there's no reason to have the little compact projector, which has a cobweb. There's no reason to have the little compact projector. You've got enough space. You could do regular. It's like, they don't care in any other room that I have a light shining in my face the whole day. They don't care in any other room. Okay. Schema. Schema is pretty important. Schema is the definition of the entire database. In SQL servers, schemas are used as containers to organize database objects. So I've also seen the term schema used to describe, you know how I said declaring a table is like declaring a function? You know, you've got attribute, data type with any of the secondary things thrown in there. I've heard that referred to as the schema for a table. So the collection of all of those is the schema for the database. Yes?
You know, when it comes to database theory, I'm noticing that there's a lot of definitions that mean basically the same thing.
Yes. Or slight differences
Yeah.
which are kind of functionally equivalent.
They all kind of step on each other's toes, something is to have multiple definitions.
See, this is this is also another interesting mathematical discussion, right? What is the complete subset of all of the definitions we've talked about, which uniquely describes every concept without repetition? Right? There. Hey, you want some homework? There you go. Question?
Thank you. I was just gonna say, so like a schema just like is the database?
Well, the database also contains the data. You can think of the schema as the template for the records in each table, right? You can think of another not terrible way of thinking about it is the header row of the table, right? So, along with associated data types and constraints. Good. All right. How many more slides we have to go? Oh,
We're only like halfway through.
no!
Pretty fast.
I hate. All right, I have to talk. Okay. I might have to finish these tomorrow. I'm sorry. Models, and you know what the problem is? I'm taking the time to explain the concepts. That's what the problem is.
You should just leave us in the dark about everything.
I should just read the slide and move on. That's what I should do, right?
I think you're a better teacher for explaining though, because like
Really?
there would be so many people who just don't understand and you would just move on with your day, but no one would have learned anything.
My perspective is that if I don't get it, what hope in hell do you have? No? So, yeah. I hope people are actually learning. I hope that the class has also been slightly more interesting than it could have been if all I was doing was reading the bloody slides. All right. I have to read the slides though. Models and database design. The process of database design is an evolutionary one in which we move through different stages. At each stage, a particular model is constructed. Number one, develop a conceptual model. Imagine yourself in the place of a person who's designing a database for a business that doesn't have one. Let's go back to, Crazy Sam's Spring Company, right? We make springs. Conceptual model. Basically, it's you and a notepad writing down all of the different entities that you need to keep track of and the relationships between those entities. Because in this example, right, cheese and crackers are entities, but tries are really only a relation between cheese and crackers, right? A try I guess it's a noun, but like it's not really a thing, you know? It's not a thing. It's a relation between two other things, right? So tables can be relations as well as entities, right? But you have to hammer out what tables and relations between tables are necessary to express what needs to be expressed. Next, you convert your conceptual model to an internal model. This means basically you take your notes that you've made about all of these database thingies, perhaps you even made an ERD, an entity relationship diagram. You made a diagram, you take the diagram and you write out your schema. You then give the schema to the database itself, and the database constructs the physical model from the internal model. So it actually goes out and does the software. So, in stage 1, for each entity, we identify key attributes and dependent attributes. Between pairs of entities, we define relationships, and this is independent of the database management system. DBMS is database management system. So at this point, we're in the realm of diagrams, right? It doesn't matter what the database is at this point. Could be a SQL Server, could be MySQL, which is the thing we should be using in this class. We then convert the conceptual model to the internal model. We take the diagram and we implement it in the system that we are implementing things in. Also known as the schema. In the internal model, the relations between entities fit the structure of a hierarchy or a network or exist as relations between tables. The internal model is required to satisfy each user view. The physical model specifies on what devices the data is stored, how the data is stored, what indexing techniques are used, and what file organizations are used. So once you've written out your schema, you've got like, how many servers do I actually have to store this? How do I get them to talk to each other, right? This is physical model stuff. Make sense? So far so good? Any questions? Okay. The relational model was developed at IBM by Edgar Codd in 1970, which is a very long time ago indeed, 55 years ago. Data is represented as two-dimensional tables or relations, yes we know. Oracle released its first database management system in '79. And they really haven't budged since then. Not really. This is kind of interesting. This is a ranking of like which ones are currently used by whom. So you can see that Oracle is the #1 database. MySQL, which open source for the win. #2. The one we're using is #3. They're like kind of comparable, you know? But if you consider that both of these are open source alternatives, I think Mongo might be open source as well. You know, there you go, there's Mongo for you. But yeah, this is an interesting thing to keep track of because it'll tell you what you know, employers are looking for, right? But yes, so relational databases can be modified. How much do we actually have left of this madness?
Wait a minute.
What if we just skip to the summary?
Terminology. Enough said. We'll cover the rest of these slides at the beginning of the lab session. Don't worry, the lab is not so onerous that you guys should still be able to finish it in the lab. Don't worry. Like the lab itself, like the part you turn in is like a Canvas quiz, so it asks you to do a couple of queries. That's mostly it. Yeah, okay, go. All right, get out of here. And we're not gonna do well, we'll do that too. We'll do it tomorrow. Like, it makes more sense to do that stuff in lab anyways because you guys don't have computers here.
Camera.